Let's talk about the diagonalization of symmetric matrices. A symmetric matrix is symmetric about the main diagonal. Here's the main diagonal. We have a 7 below and a 7 above. Here's the main diagonal. 2, 3, 5. Match these 2, 3, 5. It's just a mirror. So this is stupid. Let's talk about the diagonalization of symmetric matrices. A symmetric matrix is symmetric about the main diagonal. Here's the main diagonal. Okay, oops. Let's talk about the diagonalization of symmetric matrices. A symmetric matrix is symmetric about the main diagonal. Here's the main diagonal. We've got 7 below and 7 above the main diagonal. Here's the main diagonal. This 2, 3, 5 is going to be the mirror image of this 2, 3, 5. A, B, B, A. That's a symmetric matrix. Note that a matrix A is symmetric if and only if A transpose equals A. So the columns are the same as the rows. The rows of this matrix are 1, 2, 3, 2, 4, 5, 3, 5, 6, and those are also the columns. So A transpose equals A. Here's some non-symmetric matrices, 1, 2, 3, 4. And there's no way that this could be symmetric because it's not even square. It has to be square to be symmetric. A matrix A is skew-symmetric if A transpose equals the opposite of A. So notice, similar to being symmetric, except 7 is the opposite of -7, 2, -3, -5. It's the mirror image of these, and the opposite of -2, 3, 5. 0, -b, b, 0. That's also skew-symmetric. Here's why we're talking about this. If A is symmetric, then any two eigenvectors from different eigenvalues are orthogonal. For example, if we use Mathematica or Wolfram Alpha or the TI Inspire to find the eigenvalues and eigenvectors of this matrix, which is symmetric, we find that the eigenvalues are 7, 7, -2, and the corresponding eigenvectors are these. But the vectors 1, 0, 1 and -1/2, 1, 0 are not orthogonal. Okay, these guys are not orthogonal. Does this contradict what I just said? No, because any two eigenvectors from different eigenvalues are orthogonal. These two eigenvectors are from the same eigenvalue. These both correspond to 7, so there's no guarantee that they're going to be orthogonal. We know what it means for an n by n matrix A to be diagonalizable. We can express A in the form A equals P D P inverse, where P is an invertible matrix and D is a diagonal matrix. What does it mean for A to be orthonormally diagonalizable? It means A is diagonalizable with P, an orthonormal matrix. The columns are orthonormal vectors. In other words, we can express A in the form A equals P D P inverse, where P is an invertible orthonormal matrix and D is a diagonal matrix. Some books call this an orthogonal diagonalization and say that the matrix P is an orthogonal matrix, which is confusing because the columns are not merely orthogonal, but orthonormal. If you say that P is an orthogonal matrix, you just assume that the columns are orthogonal to each other. No, for most books, they're not only orthogonal to each other, they're unit vectors. They're orthonormal vectors, in other words. So I will call it an orthonormal diagonalization, even though many textbooks call it an orthogonal diagonalization, like our textbook that we're using this semester, David Lay's book. An n by n matrix A is orthonormally diagonalizable if and only if A is a symmetric matrix. For example, orthonormally diagonalize the above matrix A, given here. Well, the eigenvalues are 7, 7, -2, and the corresponding eigenvectors are these. D, our diagonal matrix, is going to be 7, 7, -2 along the diagonal and zeros elsewhere. If we merely want to diagonalize A, then this P would be sufficient. It's an invertible matrix. That would be fine. But we want to orthonormally diagonalize A. The first and third columns, V1 and V3 of this matrix, are orthogonal. So these two vectors are orthogonal to each other. They're from different eigenvalues, so they have to be. The first and second columns, V1 and V2, are not orthogonal. Let's find a substitute for the second vector, V2, such that the span of V1 and V2 will remain the same, but the new V2 will be orthogonal to V1. We saw how to do this in an earlier section. We express a given vector y as a linear combination of a vector u, given vector u, and a vector z that is perpendicular to u and in the same plane as y and u. So here we have y is y hat plus z, where y hat is the projection of y onto u. Here would be the formula for that. It's the projection of y onto u, that's going to be this y hat. Z is then going to be y minus y hat. So that the span of y and u is going to be the same as the span of y and z, because y is a linear combination of u and z. Okay, so here's what we had on the previous slide. Let's plug in V2 for y and V1 for u. So we're going to apply the previous principle. We have V2 is V2 hat plus z, where V2 hat is the projection of V2 onto V1. Here's the formula for that. And z would then be V2 minus V2 hat. So that the span of V1 and V2 is going to be the same as the span of V1 and z. This is so tricky and complicated. The problem we had a moment ago was that we had V1 and V2. They're just dandy vectors, but they're not orthogonal to each other. The cool thing is that we're going to replace V2 with z, so that V1 and z, the span of those two vectors, is the same as the span of V1 and V2. And what's cool is that V1 is perpendicular to z. Okay, so we saw a moment ago V2 hat is going to be the projection of V2 onto V1. In other words, we have this formula. Oh, goodness. So here's V2 dot V1 all over the length of V1 squared times V1. Sorry to mix column vectors and row vectors. In other words, we have negative 1/2 over 2 times 1, 0, 1. Negative 1/4 times 1, 0, 1, which is negative 1/4, 0, negative 1/4. So our vector z is going to be V2 minus V2 hat. And that'll be negative 1/4, 1, 1/4. So z equals negative 1/4, 1, 1/4 is in the same vector space as V1, V2. So it will be perpendicular to V3. Okay, now we're rolling. And unlike V2, the inferior vector, it is perpendicular to V1. So let's replace V2 with z. So this vector in the middle, that's no longer V2. That's our vector z. So this is the matrix P we wanted. It's a matrix whose columns are orthogonal to each other. Is P an orthonormal matrix? No, it needs orthonormal columns. So to find orthonormal columns, we need to make unit vectors in the same direction. So instead of 1, 0, 1, we want 1, 0, 1 divided by the length of 1, 0, 1. In other words, 1, 0, 1 divided by square root 2, or this matrix. This vector, I should say. 1 over square root 2, 0, 1 over square root 2. Similarly, instead of negative 1/4, 1, 1/4, we divide it by the length, and we end up with something like this, which simplifies to this, because the square root of 16 is 4, and we end up with negative 1 over root 18, 4 over root 18, 1 over root 18. In the same way, the last column, negative 1, negative 1/2, 1, when divided by the length, gives us this. Square root of 9/4 is 3/2, so we end up with this. Negative 2/3, negative 1/3, 2/3. Okay, so now we can replace those long vectors with vectors of length 1, unit vectors. Now we're done. We're good to go. That is our orthonormal matrix. So A equals this matrix. That was what we had earlier. And it turns out it equals PDP inverse, where P is this orthonormal matrix. It's invertible, it's orthonormal. And D is this diagonal matrix. And I checked that A really equals PDP inverse on the TI in Mathematica.